Hello, discrete math fans. So there's a lot of prime numbers. Look, here we go. Here's all the prime numbers up to 100. 2, 3, 5, 7, and so on. There's a lot of them. Are there more? How many more? Where do they stop? Or do they stop? Maybe, no matter how high you go, you can still find more primes. Now, Euclid knew the answer to this, and the answer is that there are infinitely many primes. No matter how high you go, you can find a prime number bigger. Now we're going to prove this. This is our second classical theorem that we're addressing in this section. We're addressing the infinitude of the primes. First, a lemma to help us out with the main proof. So the lemma says that for any integer a and any prime number p, if p divides a, then p doesn't divide a plus 1. All right, so let's suppose, for the sake of contradiction, that this statement is false. So what we are supposing then is that there is an integer a and a prime number p such that p divides a and p divides a plus 1. All right, so since p divides a, then there's an integer r such that a is equal to p times r. And since p divides a plus 1, then there exists integers s such that a plus 1 is equal to p times s. All right, let's take 1 and calculate that based on saying that 1 is equal to a plus 1 minus a. So that's equal to ps minus pr. And so if we factor out a p, we'll get p times s minus r. All right, what does that tell us? It tells us that p divides 1. But the only divisors of 1 are 1 and negative 1. And we're supposed to have that p is bigger than 1, since p is prime. Well, there's our contradiction. So what that means is that the original statement is true. So if p divides a, p can't divide a plus 1. All right, that's the end of the proof of the lemma. Now let's go on to the main proof. So the main proof, we want to show that there are infinitely many prime numbers. All right, so our proof goes like this. Let's suppose, for the sake of contradiction, there are only finitely many primes. To say that there are finitely many primes means we can write them down in a list, and that list will eventually end. All right, so let's do that. We'll list the prime numbers p1 through pn. So what we're saying is that the list of primes eventually ends. And so here is a list of all of them. Let's create a new integer. And this new integer that we're going to create, we do it by taking all the prime numbers, multiplying them together, and then in the end, we'll add 1. Now, this seems like a very curious construction, a very strange thing to do. But I think what we can show is that we'll be able to reach a contradiction out of this. Now, we know that this number we've created, this n, it has to have a prime factor because it's bigger than 1. Now, if nothing else, we can appeal to the fundamental theorem of arithmetic, that when you have a number that's bigger than 1, it can be factored as a product of primes, so it has to have a prime factor. Let's call that prime factor q. Now, q is prime, so it has to appear in our list. Remember, our list encapsulates every prime number there is, so q has to be in that list. So, by the definition of divisibility, q has to divide p1 times p2 times all the way down to pn, because q is in that list somewhere. But our lemma says that q does not divide that product plus 1. So remember that if p divides some number, if you add 1, then p doesn't divide that anymore. In this case, we're using the prime q. So we've proven now that q divides n, because we've stated that q was a factor of n, a prime factor. And we've also proven that q doesn't divide n. Well, that's a contradiction. It can't be the case that q divides n and q doesn't divide n. It's got to be one or the other. So we've arrived at a contradiction. And that proves it then. It proves that our original assumption that there were finitely many primes is incorrect, and in fact there are infinitely many primes, that it's not possible to write down the whole list. All right, so we have a proof of this second classical theorem. Again, this was known to Euclid, so this has been in existence for thousands of years. Now you get to experience this proof. I think this is another proof that's very important as part of a fundamental mathematical background, is to understand how to prove that there are infinitely many prime numbers. That's beautiful mathematics. Okay, that's all for now.